Okay, in this example, we're told we have a large compressed air tank, and we're told that it goes through a converging nozzle isentropically. That's a pretty good assumption. And the exit velocity is 235 meters per second. Let me jot that down. It's discharging into the atmosphere, which is 101 kilopascals absolute pressure. And we're asked to calculate what the pressure is in the tank, the exit Mach number, and then for part C, we're told that we're not given the exit velocity, and instead we're given the tank pressure. If we're given the tank pressure, what is the exit velocity? So that'll be part C. We'll worry about that in just a moment. We're told that the air inside the tank is at 30 degrees Celsius. That's going to be the stagnation temperature, which when we convert it over to Kelvin will be 303 Kelvin. Remember, you want to use absolute pressure and absolute temperature when you use anything that's been derived from the ideal gas law. So actually, when I work through this problem, I'm going to solve part B first and then come to part A and then do part C last. And the reason I'm going to do part B first is because I can see a connection here to find the exit Mach number. We're given the velocity at the exit and the stagnation temperature in the tank. And I know that there's a relationship between velocity and temperature. If you recall from the first law, simplified down, it'll look like this. Let me just jot it down here. So from the first law, we have an expression that looks like this. You can go back to the course notes and see how it was derived. But so I see this. There's a connection between the exit velocity and the tank stagnation temperature. I don't know so I can use that relationship to find the temperature at the exit. When I have the temperature at the exit, I can find the speed of sound at the exit, and when I have the speed of sound at the exit with the velocity, I can find the Mach number at the exit. So that was my logic for solving part B first. Is I just know that there's a relationship between temperature and velocity, so that's why I'm starting with that. So I can rearrange this equation to solve for the temperature at the exit. So that'll be the stagnation temperature, so that's the temperature in the tank, minus 1 over 2 Cp times the velocity at the exit squared. So I know my stagnation temperature, that's the 303 Kelvin. I know my exit velocity, that's the 235 meters per second. I know the specific heat at constant pressure, that's given right here. So I can solve for the temperature at the exit, and when I do that, it comes out to be 276 Kelvin. Now that I have the temperature at the exit, I can find the speed of sound at the exit. This, for an ideal gas, it's square root of kRT, and here it's temperature at the exit. So I can plug in my specific heat ratio. The K here, by the way, is the same as the gamma here. I should make a note of that. It's just the specific heat ratio. In some textbooks, they use a gamma instead of a K. The gas constant for air is given right here as well, and we just solved for the temperature at the exit. So the speed of sound at the exit comes out to be 333 meters per second. And now that I have that, I can find the Mach number at the exit. Mach number at the exit will be the velocity at the exit divided by the speed of sound at the exit. So we know both of those quantities, and you'll get that the Mach number at the exit comes out to be 0.71. So that means that the flow right at the minimum area of this converging nozzle is subsonic. So since the flow here is subsonic, it means that the pressure at the exit will be the same as the back pressure, which is just atmospheric pressure. It's given right here. So we now know the pressure at the exit because we know the flow there is subsonic. And if we know the pressure at the exit and we know the Mach number at the exit, then we can find the stagnation pressure or the pressure in the tank, right? So we have this isentropic relation, P E over P naught is 1 plus K minus 1 over 2, Mach number at the exit squared, all raised to the K over 1 minus K power. So this is a relation for isentropic flow. Again, you can refer to the notes to see how it was derived, but we know the pressure at the exit is just the atmospheric pressure. Again, remember to use absolute pressures And then the Mach number at the exit, we just solved for that. That was 0.71. So we can solve this for the stagnation pressure, or the pressure in the tank, and it comes out to be 141 kilopascals absolute. Okay, so now we've done parts A and B of the problem. For part C of the problem, oh, by the way, before we do that, it's worthwhile to draw a little TS diagram just to visually show this process. We're starting at stagnation conditions, so here's the stagnation temperature. It's the temperature in the tank. Here's the isobar. That's the pressure in the tank. That's the 141 kilopascals we just found. So here's the stagnation conditions there. And then we go isentropically to the exit. So isentropic just means we're moving along this vertical line since the entropy remains constant. And the temperature drops until we reach the exit temperature and the exit pressure. So that's what our process looks like. And by the way, we haven't reached sonic conditions. Sonic conditions would be somewhere down here. This would be T star and P star. We haven't dropped the pressure enough to reach, to reach sonic conditions. So you can see that we're still subsonic here. So if we did reach sonic conditions, you see that the pressure would be smaller and the temperature would be smaller. So that's one of the nice things about these TS diagrams, is you can visually see what's happening here. The temperature at the exit is less than the temperature in the tank. Pressure at the exit is less than the pressure in the tank. And then sonic conditions are even at lower temperature and lower pressure. Okay, so anyway, let's get back to the problem statement. For part C, we're told that the exit velocity is not given, but we are given the tank pressure of 300 kilopascals. So the first thing that I'm going to do for that is just to see whether or not the flow is choked. Okay, so the flow will be choked for a converging nozzle case if the back pressure divided by the stagnation pressure is less than or equal to the sonic pressure divided by the stagnation pressure. That sonic pressure divided by the stagnation pressure, you can refer to the notes, but that you can derive, looks like this. Basically what it comes from is this expression here, but using a Mach number of 1. If you put a Mach number of 1 in there, it looks like that. And so if the back pressure is less than or equal to P star, then the flow will be choked. Because if it's equal to P star, then that means the Mach number right at the exit will be 1. And then if it's less than P star, then if the back pressure is less than P star, then it means it'll still be a Mach number of 1 here, because that's if you're going to have a Mach number, the flow is accelerating, and if the Mach number will increase, and then the lowest the Mach number can get, or I'm sorry, the highest the Mach number can get is equal to 1, because that exit is the minimum area. Okay, so we're going to check this. If you plug in the numbers for the P star over P naught, that comes out to be 0.5283. PB for this case will still be 101 kilopascals absolute. It's still the back pressure. And we're told the stagnation pressure was 300 kilopascals absolute for this part of the problem. Okay, so when you work this out, you'll find that PB over P naught, this ratio here comes out to be 0.3367. So clearly that's less than the 0.5283. So what this means is that the flow is choked at the exit. Okay, so that since the flow is choked at the exit, it means that the Mach number at the exit is equal to 1, and all the other conditions are at sonic conditions. So the pressure at the exit's P star, temperature at the exit's T star, density at the exit is rho star. Remember that the starred conditions here just means that you're at sonic conditions. Okay. All right. So we're trying to find the velocity at the exit. Since I know the Mach number at the exit's 1, let me use that. So remember that the Mach number at the exit's the velocity at the exit all over the speed of sound at the exit, where the speed of sound is the square root of kRt, temperature at the exit. I know the temperature at the exit's T star, right? We Just talked about that a moment. I know the Mach number at the exit's 1. So the velocity at the exit will be square root of kRt star. To find the sonic temperature, I can go back to this relation right up. Well, I guess I didn't write it. Let me write it down here. So T star over T naught is 1 plus K minus 1 over 2 to the minus 1 power. This comes from, again, the course notes. It's basically an expression that looks similar to this one, but for temperature, and then again, making the Mach number 1. We know the stagnation temperature is still the 303 Kelvin, right? That's still given right up here. So we can solve for T star. And T star comes out to be 253 Kelvin for this case, which then means that we can solve for the velocity at the exit, which comes out to be 319 meters per second. Okay, so that is how we solve for part C. So the key thing for this last part is determining whether or not the flow is choked using this expression. Remember, this expression only holds for converging nozzles. It does not hold for converging and diverging nozzles. And to understand where this comes from, you have to go back to the course notes and where we talk about this expression. Now, just to kind of, we weren't asked to do this, but just to show you what you would do if the flow was not choked. So let's say we were given a tank pressure that was smaller than 300 kilopascals, such that this ratio was greater than the 0.5283. So let's say it came out to be 0.6, for example. Okay, in that case, the flow would not be choked, which means that the flow at the exit would be subsonic. If the flow at the exit is subsonic, then the back pressure and exit pressure are the same. Once you know the back pressure, or once you know the exit pressure and the stagnation pressure, you can use this expression to get the Mach number at the exit. So you would have the exit pressure, that's the back pressure. Tank pressure is given, that's P naught. You could solve this for the Mach number at the exit. And once you have the Mach number at the exit, you could find, for example, the temperature at the exit using an expression that looks like this, similar to what is written right above it. So you could use this expression to find the exit temperature, because you know the stagnation temperature and the Mach number at the exit. Once you have that the exit temperature, you could find the velocity at the exit, or the speed of sound at the exit from this, and then the velocity at the exit using the Mach number relation. So that's what you would do if it turns out the flow was not choked. If it's not choked, the key piece of information is that the exit pressure and the back pressure are the same. If it is choked, then you know that the exit pressure is equal to P star, and the Mach number is 1 there. Okay, we'll go ahead and end the example there.